So as you know, this basically distillation process, binary distillation process, quiz number 1, involves two main procedure. First one is to obtain the minimum flux ratio, and then you use this minimum flux ratio to obtain the actual flux ratio, and you use punch and Sabri method to obtain the number of stages. So I don't know, do you know if they have any problem? Why not everyone is here, or it is just, do you have any idea? Do they have exam, the other students, or no idea? Okay, so this is the problem. Basically, the mixture of 100 moles per hour contains 45% benzene and toluene. So I have a mixture of benzene and toluene to be separated by distillation into a liquid distillate containing 96% benzene and 96% toluene in the bottom. So you have to be careful. Here is the bottom composition of the more of the heavy component, which is toluene. So I have X feed here. I have XD here. I have 1 minus XD here. So now I can get here from this one, I can say XW1 minus 0.96, which is going to be 0.04. Feed is 50% vaporized, and this is the major source of error for most of the students. So 50% vaporized, that means Q here is, well, 1/2. They give an external reflux is equal to 1.5 R minimum. So from this one, you can see here, R actual is 1.5 R minimum. So you have to determine R minimum, even he's not telling you to do that, but you know, you have to do it. You have to obtain it first. Calculate the number of stages using punch and Sabri method. And also calculate the condenser and the boiler, the loads in kilojoule per hour. And you are provided with, as you see here in the table, you are provided with the equilibrium data X and Y. And at the same time, you are provided with, for example, this one, you have the h small l as a function of X. You have this one, which is H capital, which is the saturated vapor enthalpy as a function of Y. Okay, so now we have to proceed. As you know, we have to get the minimum reflux ratio first. Now, before we can do that, we have to calculate the molar flow rate. So if we go back here, so these are the given information. You have the feed flow rate, so you have distillation column, and the boiler, total condenser. Feed is 100, and you have X feed here, XD here, and W is not given, but I know XD here is equal to 0.96, XW is equal to 0.04, and here it is very straightforward, I guess. We have 100, this is the first equation, is equal to D plus W. And I have 45 here is equal to D 0.96, D plus 0.04, W. This is equation 2. Now, if you solve these two equations simultaneously, you can easily obtain the flow rate or the mole flow rate of D and W. And this is the answer here. So I don't think we have to spend too much time to solve this one, because this one has nothing to do with any of the contents or any of the learning outcomes of this course. يعني هذه أشياء لها علاقة بالmass balance. But as you see here, it's something that you have to do before you can start solving the rest of the problem. Is this clear, guys? Any question here? Right. The second thing now, so we have to first get the smaller flow rates of the distillate and the product. Now the second thing is to get the R minimum here. So how are we going to be able to determine R minimum? Now we have different approaches, but the only approach that we covered is using the McCap-Tape method. And as you see, we said we have two equations. And these two equations, this one is as you see here, this is for the operating line of the top section. And this one is the Q line. And we said all what we have to do is just to draw the equilibrium data. And then you will have to draw, now this is your XD, of course. And this is your XF here. This is your XW. This one is equal to 0.45. And this is 0.96. Now, in order to determine the minimum, you don't have to worry about the bottom section here. So all what you have to do, first of all, is to find out the equation here, the slope of this one. Now, based on Q, since it is 50%, so that means it is 0.5. And now we define Q as the quantity or the fraction of liquid in the mixture. And if you go back to the statement of the problem, it says 50% of the feed is vaporized. So now we have Q. Therefore, I can say Y is basically the Q line. It's going to be Y is equal to 0.5 over what? Minus 0.5. X feed is basically 0.45 over minus 0.5. So you're going to have something like minus X plus, I don't know, 45 over 2. That means this 2 multiplied by 45, that's going to be 0.9. So this is your equation. And now we know the Q line is one of the points that is going to be passing through this Q line is going to be the X feed. So this is the first point that you're going to say. It's going to be 0.45 and 0.45. The other point can be determined from this equation. And I can tell right now this one is from 0 to 1, and this one from 0 to 1 also. Now, if you look at this line, at x equals 0 here, at this point, y is equal to 0.9. So you can have another point. So the first point is going to be 0.45, 0.45. The second point is, because you wanted to draw a straight line end of the day, it's going to be 0 and 0.9. So basically maybe somewhere here. So this is your second line. So you can draw this line. It doesn't have to be this point, by the way. You can choose any point. Some other people will say, instead of having 0 and 0.9, I can have another point, maybe let's say 3. And what would be this one? If you choose x to be 0.3, what would be y here? Any idea? If we choose x to be 0.3, if we choose another point, now this is clear here. This is 1 point. maybe there's another point here, another point here, another point here, lots of points. You can infinite number of points. Now let's assume you're going to choose this point here. What would be y here? If you choose, yeah, 0.6. So basically it's going to be 0.6. So now it's up to you whether you want to choose this one or this one. It's up to you. Now you have the scale ready. 0.6 has got to be somewhere here maybe. So what at this point or this point, the line will pass through each of these. Once you have done, you are done with the Q line. Now you will start the first point drawing this operating line. Now, in order to draw the operating line, you need R, but you don't have R. You want to determine R based on R minimum. But you know the first point that is going to pass through this line is going to be this point here. Now, in order to determine R minimum, you have to draw a line, a straight line of this operating line, as you see here. But that line must cross this equilibrium line and the Q line. Okay? And in this case, it's going to be somehow like this one. It must go, or it must pass the intersection between the Q line and the equilibrium line. And that will represent the slope at minimum condition. Or let's say that R, because R here is going to be, if you want to measure the slope, is going to be this slope here is equal to R minimum over R minimum plus 1. Okay, so I have two options. Either I can use this one, or I can go straight to this line here. And I say here at this point, what this point is going to represent, it's going to be at x equals 0. When x is equal 0, y is equal to xd over r plus 1. So this one will be xd over r. Now, because it is, this line is drawn at the intersection, will represent r minimum. Now, this one, you can read it from the graph, that number, and you have xd, you can get r minimum. So you can get r minimum is going to be basically the intercept. We'll call this one intercept here. Okay. Okay, this will the xd over the intercept here minus 1. خلاص, now you got R minimum. All what you have to do is say R actual is going to be 1.5 R minimum. Any question regarding this one now? We will show you the grade distribution later on, guys. We'll explain the grade distribution. Now I want you to just understand so you don't repeat the same mistake. You see here, so sometimes it's very small, little details, but if you make a mistake, you're going to damage all the rest of the calculations. Okay, so now we have the R minimum. So as I explained here, Q is equal to 0.5. Now you can start with this Q line here, equilibrium curve, and then you have this point here, as we said here. This is the first point, which is going to represent the feed. And this is another arbitrary point that we choose based on this one. So that would be your Q line here. So this is your, and you know the XD here. This is your XD. This is going to be 0.96. You draw it, so you draw it in a way that is going to cross both the equilibrium line and the Q line, and that intercept, which is 0.34, the one that you get to use at minimum condition here. From it, you can determine R minimum to be 1.82. Okay, so R minimum was 1.82. This is the first thing. So we determined R minimum, from which we can get R is equal to 1.5 R minimum, and this one is given in the statement of the problem. Says it is 1.5 R minimum, by the way. So now here is the R actual that you're going to use to determine the actual number of stages. Okay. Any questions? Now you see here the distribution of the grades. As you see, plotting is going to have 2 points because, and the way how you determine, or like for example, as we will show you inshallah for the grade distribution, I have grades for the number you obtain, R minimum, and there's also grades for the drawing. Now, it's not only just the final answer, but also you will be graded in both the drawing, because it will take some time, and also the way how you calculate. For example, if you draw everything is okay, now that will, for example, if you draw this line here correctly and you have the intersection point here, and you draw the Q line also in the right position here, you will get 2 points. But now if you make mistake in determining the intercept, and because of that you get this one wrong, so this one will not be counted. So you will get 0 for this one and 0 for this one. Okay. Any questions so far? Clear? Right. Now I have minimum and I get the R. Now I will go and use now punch and summarize. Now the trick thing here. And this is really important. Students, they start drawing without knowing their scale. Now, in order to be able to determine where exactly you are, if I ask you this question, I have what's called OD, and I have OW. And I think this one represents the maximum in the scale. Maximum point in the enthalpy chart. And this will represent the minimum value in the enthalpy chart. So, because if you remember, we had something like this before. As a quick here, we said we have, this is the enthalpy. We have here OW, sorry, OD here. And we have OW, and we have each feed, doesn't matter where exactly, but it is at XW, XD, and X feed. Now let's assume the feed is somewhere here. So now I have a line that's going to connect all of this one. If the feed is saturated liquid, of course. So now I want to know my scale here, so I have to be careful now, because if you start generating the scale before you know where exactly your OD, or at least rough estimation of your OD and OW, you might not be able to draw OD, because maybe you will take the scale or the maximum value of each enthalpy of the vapor and the liquid, and then you will not be able to locate OD, or the OD value is beyond the scale that you generated based on the enthalpy data you have. So now, first of all, let's try to determine the terminals of my scale. This is important. Now I have this R is equal to OD minus H1 over H1 minus H0, and I know R now, already determined it. So I have only one unknown in this equation, which is OD. But now H1 and H0, as you probably know, when we have a distillation column like this one, this is the first stage, stage number 1. So this is the vapor, so this is V1 here, and it is going to go to the condenser here. And this is X0, and this is XD, and let's say this is Y1, of course. Now, when we have a total condensation, as we mentioned before several times, the quantities, the flow rates, of course, of V1, for example, and this is L0 and this is D, V1 is not the same as L0 and D, they are different. But the composition, or the mole fraction of the more volatile component, and the vapor leaving last stage here, which is this one, is the same. So now I have Y1 is equal X0 is equal to XD. Why? Because we have total condensation. Now I will use this information or this fact to determine H1, because I know H1 is what? Is the enthalpy of vapor, saturated vapor, of course, at Y1. Now Y1 is equal to XD from this fact. H0 is the enthalpy saturated liquid at X0, which is equal XD. Okay. Now, is this clear, guys? Do you have any objections here? Okay, so you agree all? And this is only for total condensation, of course. Where do we get the H1 now and H0? What do you think we're going to have, or how are we going to be able to determine H1 and H0? Any idea? Any idea, guys? Where do we get H1 and H0? How do we get this H1 and H0? Any trial? Okay, so we have enthalpy of vapor at XD, and this is the graph you're going to use, and this is your XD is equal to 0.96, and then you can go to H1, Y is equal to XD, can get it from by interpolation, you can get H0 is equal to minus 16, substitute in the equation with all these variables, and that the flux ratio. Now you can get XOD from the equation, and this is going to represent the maximum point in the enthalpy scale. You do the same thing now for each feed because it's 50% vaporized, and then you know from thermodynamics 50% vaporized means it's going to be somewhere here. We don't know where exactly, so we have to determine this one. If you go back to chain 1200, you can obtain the enthalpy of the feed, which is going to be the enthalpy of the liquid, saturated liquid, at X feed, plus the lambda, which is the heat of vaporization, multiplied by 0.5 because it's 50%. Now this is also important because you'll need to determine the enthalpy of the liquid at X feed. So you have X feed is 0.45, so you're going to be somewhere here, and you have to go to this liquid here. You do some approximation, linear interpolation of whatever you want to use, so that enthalpy or delta H of vaporization is going to be the enthalpy of the saturated vapor minus enthalpy of the saturated liquid. That will represent lambda, and both are at X feed here, as you know. Now you go to this to get the enthalpy at saturated vapor at 0.45 here somewhere. And sorry, that would be here at 0.45. That means it's going to here. Sorry, because this is your Y for the HV. For the H liquid is going to be between this one and this one. So you have two scales here you can use. Now, if you do that, you can get this HV and HL from the graph, and you can get the enthalpy of lambda here. We call it lambda, as it's determined here. So you have HF is equal to 2.5, and that was the major mistake of most of the students. Now I have H feed and I have OD. What you have to do now is just before you go here, this is your scale here. So now you have H feed and OD. Now you have the slope of this line is equal to the slope of this line. So you can use this geometry. OD HF. This is the slope of this line here is equal to the slope of the line between this point and this point, because the slope is the same here. Now all you have to do is just to substitute these numbers here, so you can get W here. You know the H feed now it's already determined. You know H feed here. OD is already also determined, and you know the feed XD, XF, XW. From which you can get OW, and that will represent the minimum point in the enthalpy scale. So now you know what is exactly the maximum number in your scale in the enthalpy chart, and the minimum. You can do that very simple with this one, and with the data here. You have the scale. So you see here we have the maximum is 96, so we can start from the maximum point 100, and the minimum is minus 73, so we can use minus 80 as the minimum. Now I can draw my data here, so I can draw between this one and this one, and between this one, this one. So I have two lines, as you see here. This is going to represent X, this series, and this will represent HV. So this one is basically HL, and this one is going to H capital V. Now you have OD and XD. You can determine from this one. This is zeros, as you can see here. So this is your XD and OD here. This is your OD, and then you have your feed point, which is at X feed at this 0.45, and H feed, which is 2 point something here. This represents H feed here. And then you can connect these 2 points. You can get OW simple by crossing this. This is XW here. So this will represent OW, which is exactly or almost close to minus 73. Now you will start drawing this data. Now you start from here to draw the first tie line. Now the first tie line will represent the first stage and so on. So you connect it with this one. That will represent Y1 and this will be X1. You connect X1 with OD, you can get Y2. Y2 can be used to the equilibrium line to get X2 and so on. You do that, and then each time you move to the left until you cross the, as you see here, the feed. Once you cross the feed, you'll have to switch now to the OW. OW means you're going to connect this one with OW and so on, and then you can get the other points as well. All of these are the tie lines, so you can count 1, 2, 3, 4, 5, and so on until you reach this last point here. Now, maybe you will ask yourself how I get, if I come to Y1, where I get, how I get X1? Yeah, it's very simple here. It is just go back to the diagram, you use it to draw the equilibrium line. So these are the points that connects. For example, this one is going to represent this one. This one will represent this one, and so on. Okay, so these are the tie lines, or the tie lines that connects between X1 and Y1 and X1, Y2 and X2, and so on. Any questions so far? I think it's clear, hopefully. So now I think we are done with this one. No more questions. We can go and try to find now. I got the number of stages, and as you can see here, the plotting has 3 points. Getting the number of stages will have 4 points, so total is going to be 7 points. Now I will try to determine the report on condenser duties. Now, as you see here, if you go back to the diagram, it's also something related to thermodynamics. Now, this is one is going to be saturated vapor, and this one is saturated liquid. So now QC is basically, this is your QC, for example, will be, this is your V1, huh? It's going to be V1 multiplied by delta H of vaporization, okay? Now, what is delta H of vaporization? Delta H of vaporization, in this case, is going to be H1 minus H0. Why I'm saying H1 minus H0? Because this is going to represent saturated vapor, which is at 1. So this one at X is equal XD, by the way. And this one will be at X equal XD as well. And this one, sorry, what at Y here. If you do that, you can get the QC very straightforward, because we already know these two values from the beginning when we determined OD, if you remember. But I don't know V1. How are we going to be able to get V1? Can get L0, which is, this is going to be L0, and this is D. Now I know L0 is R, because I know R is basically L0 over D. So I can get L0. And if I add L0, which is to D, I will get V1 here. This is simple, I think. So V1 is going to be 166.57. And multiplied by the delta H of vaporization, which is determined from H1 and H0, already calculated, already located in the diagram, multiplied by V1, I will get QC. Now I have QC, how I get QW, or reporter duties. You know the column, it's like this one. This is feed, and this is H feed. And this is the QC, and this is D, and let's say H0. And this is W or bottom, let's say bottom, and each bottom here. Okay, and this is your QR. So now if I write the energy balance around the system, I will have energy in is equal energy out. Now, how many energy ins we have? We have to count for all streams going to the system. If we take this as my system, this is also thermodynamics. So I have inlet here, so I have H feed multiplied by feed. What else we have in? We have Curie boiler, because we are heating, so we have to say QR plus QR. This is energy in is equal energy out. Energy out, I have QC is out because we are cooling, so that we are removing heat from the system, plus the flow rates of the two streams. So we're going to say D multiplied by H0 plus W or bottom multiplied by HW here. Okay, so now if you do that, you only have, and this is going to be representing H out, energy out. You have everything except QR is not given, so you can calculate it simple. Now you have to be careful now when you H0 is clear, this one, but HW, what would be HW, guys? How we determine HW? Do you know? Or at least do you know how to determine HW? No idea? Sleeping, guys. It seems like you are sleeping. Okay, so it's W is basically, as you know, it's going to be the liquid, because this one is liquid here. So this one is liquid, so I have to go back to the chart, and I come here, and this is my HW. Okay, why? Because it's liquid, and it is at this W. If I know that, B is already determined, the flow rate of the bottom and the flow rate of the liquid here. H0 is going to be here. This is going to be H0. H1, this is H1. Okay, that's all. And this is my HF here. They all can be read from this diagram. Clear? Yes, that's right. So now we go to the last thing here in this lecture, and this is the flow, the Mach distribution. Total Mach is 18. You see here flow rates. You calculate the mass flow rate, 1 Mach. Plotting the equilibrium data. The first one is 3. Draw the Q line 2 Machs. Determine R minimum from the graph is 2 Machs. R is 1 Mach, which is just 1.5 R minimum. OD, the first point is 2 Machs, because you need to use the equation. The NW, so the number of states is going to be 4 Machs. OW is 1 Mach, and then QC and QR 1 Mach, 1 Mach. Hopefully you learn from your mistake. I think the only challenge or the only trick here in this problem was the feed is not saturated liquid or saturated vapor. Some few made it completely wrong, because they drew the line of the drew the Q line completely different, without any inclination or without any slope. So that was completely wrong. The good news is that you can improve in quiz number 2, because it's going to be on multi-component distillation, and I guess it is the easiest topic in this course. You all just be dealing with equations. Just be ready. It's going to be next week, of course. Try to discuss few issues regarding the multi-component distillation, inshallah, in this tutorial today. Maybe we'll solve another problem and show you how to use the solver. We will take the best, I think, quizzes, 3 quizzes. Maybe we will have 4 quizzes, and we will take maybe the best 3 quizzes. That's what I think we discussed with Dr. Arfan. Since this quiz is not really good, yani, صراحة. So there's still a chance for you to improve yourself. I don't worry about it. I know it is the most difficult, probably, topic in this course, this bunch of separate method, especially when it is involving determination of the R minimum, and if the feed is not saturated liquid or saturated vapor, and when it is mixed between these two. More difficult if we're going to have it subcooled or superheated, but try not to usually complicate things during the quiz time. But since the calculation of the H feed didn't really require that much time, if you know the idea, by the way. But if you don't know the idea, then it's going to take ages. Or some students, they just ignore this fact and they draw the H feed exactly on the saturated liquid line, and that was a fatal mistake, to be honest, because everything else will be completely wrong. And the calculation of the number of stages, the counting number of stages will be affected. Not that, but also OW will be affected if you change the location of the H feed in the diagram. If there's no more questions, I think I will stop and see you inshallah in the tutorial session. Any questions? Okay, then I'll see you inshallah at 2 o'clock. Hopefully we'll see more of you guys here. It's 5 students only, 4 students only here at 8:51. So it means I don't know, and then they will start to complain once they fail in the quizzes, students. I don't know, but anyway, so we'll see you inshallah at 1 o'clock, I think, or 2 o'clock. No idea. Okay. Okay. See you. See you 1 o'clock, inshallah. Thank you very much.